Section 10.4 is a short section on the AEP for continuous random variables. In this section, we will develop the AEP for continuous random variables in the same way as we developed the weak AEP for discrete random variables. Theorem 10.35 is the AEP1 for continuous random variables, which is exactly the same as its discrete analog, except that the probability density function is now in place of the probability, and the differential entropy is now in place of the discrete entropy. Again, the AEP for continuous random variables is a consequence of the weak law of large numbers. Definition 10.36 is the definition of the typical set and typical sequences. Again, this definition is exactly the same as its discrete analog, except that we now have the probability density function in place of the probability and the differential entropy in place of the discrete entropy. Accordingly, we define the empirical differential entropy with the probability density function in place of the probability, and according to definition 10.36, the differential entropy of a typical sequence is close to the true differential entropy of the generic random variable x. The only difference for the continuous case is the interpretation of the size of the typical set. For the discrete case, the typical set consists of a finite number of typical sequences. For the continuous case, the typical set is a subset of the nth-dimensional Euclidean space, which consists of an uncountable number of typical sequences, and hence its size is measured by its volume. We first define the volume of a set in the Euclidean space. For a subset A in the nth-dimensional Euclidean space, the volume of A is defined as the integral with respect to dx over the set A. Theorem 10.38, which is the AEP2 for continuous random variables, says that the following hold for any epsilon greater than 0. First, if a sequence x is epsilon typical, then the probability density function of x is very close to 2 to the power minus n times the differential entropy of x. Second, for n sufficiently large, the probability that the random sequence x is epsilon typical is greater than 1 minus epsilon. And third, for n sufficiently large, the volume of the typical set is approximately equal to 2 to the power n times the differential entropy of x. Here are a couple of remarks. The third part of AEP2 says that the volume of the typical set is approximately equal to 2 to the power n times the differential entropy of x when n is large. We would like to point out that the fact that the differential entropy of x can be negative does not incur any difficulty, because 2 to the power n times the differential entropy of x is always positive, even when the differential entropy is negative. If the differential entropy of x is large, then the volume of the typical set is also large.